I am usually happy to talk about climate with anybody that's willing to listen. And so when Professor Newbig reached out to me about talking here today, I was very quick to agree to do so. And I've been around all afternoon and heard many other interesting presentations. And my goals here really are two. The first is I'm aware that many of you are probably aware of the major kind of issues governing climate at the global scale, but there may be some people that aren't. And even if you are aware of those changes, it's always nice to have an update on the current science. So I'm happy to provide that to people. I'm also interested in kind of bringing global change to the regional and local scale as the introduction kind of suggested. So my research as a geographer is really about scale interactions in the climate system and how things occurring at one scale might influence processes that are happening at other scales. Let's see. Yeah, we're good. You did it, Kurt. Okay. So the talk is really going to have three parts. The first is kind of a general overview of climate science. The second part is going to be an overview of recent historical changes, both at the global scale and more regionally. Those first two parts are really the bulk of the talk, about 90%. And then I'll just finish up at the end talking a little bit about what we can say about future climate and how that's likely to add on to the kinds of climate changes that we're already seeing in our area. Oh, by the way, this is a very famous image. This is the blue marble image that many of you are probably familiar with. This image was captured by astronauts on Apollo 17 in 1972. And I included it in a lot of my talks because I think the reasons that this image became kind of synonymous with the environmental movement of the 70s and 80s is that it really does demonstrate the fragility of the system, the complexity of the climate system as it relates to clouds, open areas, land, ocean, etc. But also I think that it represents the isolation of Earth and space. And we have a lot of ideas that we hear about these days about colonizing other planets and that sort of thing. And if there's one thing you take away from my presentation, I hope it's that there is no planet B. Earth has all of the climate characteristics that we need to survive as a species and that we need to thrive as a species. Other planets just don't. Very simple. Okay, so I start most of my talks with some image that looks like this. This is a kind of simplification of the climate system. The climate system has 5 primary components that are shown here. And we typically think about climate as being kind of the response of the atmosphere to all of these other components. So all of them are really interesting and complicated on their own, but the climate system is made more complicated by the interconnections between the climate system components and their different reactions across time and space. So for example, the atmosphere is a very fast responding part of the system. We can experience this ourselves, right? When you wake up in the morning, as soon as the sun comes out, there's almost immediately measurable change in temperature. It responds very, very quickly. And that actually is a process, right? The sun doesn't heat the air. The sun heats the surface, which then heats the air. So that process actually takes place very, very quickly when the sun comes up. Changes in other parts of the system are much slower. So if we think about changes in the ice sheets, changes in the deep oceans, for example, these are changes that take much, much longer to take place. So not only do we have different systems, different subsystems within climate, but they have different response times and different characteristics as well. So when we think about climate change, we can think about climate changing when any of these individual components change. This is true for both natural and anthropogenic climate change. But we can also think about interactions between the components, and we can think about things like climate feedbacks, which are actually very important. For those that aren't familiar, climate feedbacks occur when system processes either reinforce a change or take away from the change. So 2 very common examples that are really important for our future climate are, 1, ice albedo feedback. Ice is highly reflective. The underlying ocean is usually not very reflective, especially when the solar angle is really high. So if you start melting ice and all it has beneath it is dark ocean, right, then that results in more absorption of solar energy, which results in additional heating, which results in additional melting. By the way, that process works in the opposite direction too. So if you cool the planet, you get more ice, which is more reflective, which further cools the planet. We also have a positive feedback from water vapor that's very important. So as you warm the climate due to carbon dioxide, you increase evaporation from the oceans, and water vapor is also a strong greenhouse gas. So it turns out that when you increase the atmospheric carbon dioxide, a lot of the change that you get isn't from the carbon dioxide itself, it's from those climate system feedbacks that act once carbon dioxide has changed the temperature. So if we want to think about changes, changes can be naturally driven, they can be anthropogenically driven, they can be internal to the climate system. So we can think about things like ocean atmosphere variability. We could think about things that are external to the system. So I'll point this out a little bit later in the talk, but we can actually see a small signal in climate related to the 11-year sunspot cycle. It's very small relative to changes we're seeing from greenhouse gases, but it's still there. It's measurable. So we have both external drivers and internal drivers of climate variability and change. So at the most basic level, we can think about global scale climate change as really being a response to changes in the global energy balance. So this is a figure that is quite complicated, although versions of it appear in just about every introductory weather and climate textbook. This is actually really hard stuff to measure, and it would have been impossible to measure before the satellite era. So what we're looking at here is the amount of energy that enters the Earth's system and the amount of energy that leaves. And so the near surface energy balance could be thought of as relating to how the incoming energy might be changing and how the outgoing energy might be changing. Fundamental to Earth's climate is that we receive energy and lose energy in different forms. I want to make sure we get this right. The Earth is receiving energy across a range of wavelengths, but primarily in the visible part of the spectrum. We get most of our energy from the sun in the form of light. The Earth, though, is not emitting any light of its own. If you were standing in space and you didn't have reflection from the sun, you would not see Earth, right? We see it because of reflected light, not because it's giving off light energy of its own. So the Earth is losing energy in the form of heat. The transformation of that energy at the Earth's surface is a fundamental characteristic of our climate. So in other words, we absorb solar energy at the surface, and then the surface actually loses that energy as heat, not as light. So it's the fundamental difference in the way that our atmosphere responds to incoming and outgoing energy that really is the basis of our climate system. So when we think about non-reflected solar energy arriving, that's what we're really showing on the left side of this diagram. And so you can see that basically about a third of what arrives is just reflected back to space, either by clouds or by the surface. The other 2/3 comes into the system, and about maybe a third of that is absorbed in the atmosphere. The other half or so makes its way to the surface where it's absorbed. So our atmosphere is relatively transparent to energy from the sun. That means a lot of that energy is able to make its way to the surface where it'll be absorbed. Anytime you have absorption of radiation, you have an increase in temperature. So that absorption warms the surface, which in turn warms the lower atmosphere. Now, when the Earth loses energy, things are a lot more complex. And that's actually shown here on the right side. So in addition to losses through radiation, we have these things in the middle like thermals and evapotranspiration and so on. Those are other ways that energy is removed from the surface of the Earth. But if we just focus for now on the radiative part, what we see here is the greenhouse effect. That as energy is lost in the form of long waves, really in the form of heat, gases in our atmosphere are really effective at absorbing. They're not effective at absorbing the sunlight, but they are effective at absorbing the heat. So again, that transformation at the Earth's surface is really, really critical for understanding the energy balance of the planet. I want to point out that this is actually very important in a natural context. if we didn't have an atmosphere, our planet's surface temperature would be somewhere around 0 Celsius, okay? So we have the greenhouse effect in a natural context to thank for making our planet livable for us. It's only in a contemporary context that we've kind of accelerated the rate of carbon movement between reservoirs in the system and enhanced the greenhouse effect, so that we're now moving carbon between these systems at very rapid rates. So if we want to be able to say something about anthropogenic climate change, we have a couple of key questions. Number one, how well do we understand natural changes in the global energy balance? The answer is actually pretty well. How do we know? Well, we've done experiments in recent years with things like volcanic explosions. So we know when we have an eruption that we tend to get a cooling, and we can use the cooling to do things like estimate the sensitivity to, well, for example, the water vapor feedback. So after Mount Pinatubo erupted in the Philippines in 1991, the global temperature decreased by about 0.5 degrees Celsius near the surface. It's a large temperature decrease. And as a result of that, we actually saw the next year about a 3% decrease in atmospheric water vapor. So that's actually consistent. We expect actually atmospheric water vapor to increase by about 7% per degree of warming. So 0.5 degree of cooling and a loss of about 3% actually makes pretty good sense relative to what we would have expected. We also have a pretty good understanding of how carbon moves through the climate system during glacial and interglacial periods. It turns out that we have about 90 parts per million more carbon dioxide in the atmosphere during interglacials than we do during glacials. And the question is, well, where does that carbon go? It doesn't stay on the land surface because during an interglacial, you have less land, right? Sea level's higher. So we know that it goes to the ocean. And in fact, at least to the intermediate depths of the ocean, probably through a biological carbon pump. So we have a pretty good understanding of what's going on in terms of natural variations in energy balance. Number two, though, how well do we understand anthropogenic changes in the environment that affect the global energy balance? Well, we certainly understand the larger ones, right? We have a pretty good understanding of the effect of carbon dioxide, for example, on the energy balance. There are other parts that we're considerably less certain about, and so we'll talk about some of those in a few minutes. And then third, how well do we understand the climate changes that will result from those environmental changes, right? The answers to all three of these questions are, well, pretty good, but not perfect, right? So we have a long way to go before we have the ability to, really confidently discuss the evolution of the climate system in a high level of detail. So we refer to these as anything that changes the energy balance that's displayed here, we refer to as a climate forcing. And it's kind of an unusual term to use, but what it means is that if we change the inputs or outputs that are shown here in watts per meter squared, what we're going to do is force a change in the climate. And so we've spent a little bit of time here talking about the greenhouse effect, but what else is going on? This is a figure from the latest IPCC report that shows what we really know about radiative forcing. And so anything that is positive on this figure is going to result in a warming of the system. And anything that's negative on this figure is going to result in a cooling of the system. So I'd like to just kind of walk through these and talk about what the major issues are. And by the way, this goes back to, I think this is total anthropogenic since 1750. Yeah. So the top line there is carbon dioxide. And you can see, we know very confidently that carbon dioxide has a large positive radiative forcing. You can also see on the end there, scientists like to use error bars to give a sense of how confident we are in a result. And so you can see there that the effect of CO2 is known pretty well, right? The error bar is small, so we know that's going to have a fairly large effect. Below that, we have the other well-mixed greenhouse gases. So those would be things like methane and a few others. Methane is a very important greenhouse gas. It's on a molecular level stronger than CO2, but it doesn't stick around very long. Methane's oxidized pretty quickly in the atmosphere. So it has a much shorter atmospheric lifetime than CO2 and is present in much smaller quantities. Below that, you can see ozone. So we tend to think of ozone either in terms of its presence in the stratosphere, which protects us from ultraviolet radiation. Here, we're primarily talking about ozone in the troposphere, so as a pollutant, which also acts as a greenhouse gas. You can see stratospheric water vapor here. That's actually mostly from oxidation of methane. So when you oxidize methane in the troposphere, most of the water vapor is washed out as part of the hydrologic cycle. But if you oxidize methane in the stratosphere, those precipitation processes aren't present. And so that water vapor can stick around, and its greenhouse effect then is useful here. You can see effects from albedo actually change in both directions. So on the negative side there, we have changes from land use. So how would land use result in cooling of climate? Well, we're not really talking about carbon storage in the land here. We're talking about changes in the energy balance from the reflectivity of the land surface. If you take a forest and you remove all of the trees, the underlying surface may actually be more reflective than the trees were. And as a result of that, you affect the radiation balance in a way that results in a cooling. On the opposite side of that, you have the effect of light-absorbing particles on snow and ice. So one thing that we don't talk about very much is that combustion of fossil fuels also produces a lot of black carbon. And that black carbon can gravitationally settle onto ice sheets and snow surfaces and things like that, where not only does it absorb sunlight and make the snow and ice melt faster, right, but it also makes it less reflective. So there are some important implications there. Below that, we have contrails and aviation-induced cirrus. That's exactly what you think it is. So when you go outside on a sunny day and you see those aircraft contrails across the sky, those basically act like a high-level cirrus cloud, which has a positive radiative forcing. In other words, our climate is warmer with aircraft contrails than it would be without them. Okay, and so high cirrus clouds have that effect, that they generally warm the climate. By the way, just as a kind of interesting side story, a lot of the work on aircraft contrails and climate was done following the 9/11 terrorist attacks. And some of that work was actually led by faculty that I was learning from when I was an undergraduate in Indiana. And they were the ones that initially published the work that quantified this effect. So below that, we have a large negative forcing, which is from aerosols. So aerosols are about 90% naturally occurring. This is actually referring primarily to the effects of anthropogenic aerosols. A lot of this is sulfate. So we have sulfur dioxide that is a byproduct of many of our industrial processes. And the uncertainty around aerosols, as you can see here, is the largest in the system. And that's because aerosol interactions with clouds are very complicated, right? We're talking about microphysical processes that determine, whether individual cloud droplets are activated and continue to grow. I think generally there's an underappreciation of the role of chemistry in precipitation processes. And so we're likely to see some impacts there. That darker blue chunk there under aerosol radiation, this is where aerosols basically block solar radiation from reaching the surface, much as they would following a volcanic eruption. The bottom line here is the total anthropogenic effect, which you can see is about 2.72 watts per meter squared since 1750. So if we just look at CO2, which is the primary culprit that we're used to thinking about in the context of climate change, this is what conditions look like since measurements began at Mauna Loa in 1958. So this is the longest instrumental record that we have of atmospheric CO2. Interestingly, the observatory had to be temporarily shut down during the eruption last year, which actually washed out part of the road. I don't know if you'd call it a washout when it's flowing lava, but anyway, the access to the observatory was lost for a short period of time. But I think the backup instruments continued to measure the CO2. Anyway, what you see here is this drastic increase in atmospheric CO2 since the late 1950s when these measurements were taken. It seems like it was just a short time ago, because it was, that people were talking about, hey, we're going to hit 400 parts per million, right? Well, now here we are just a few years later, and we're firmly at 420 parts per million with no sign of slowing down. I'll point out that this is also a nonlinear increase, so that each year we're getting a little bit more CO2 added to the atmosphere than we did the year before. Now, this record, 60 years or so, is fairly short in the context of climate science. So I found this wonderful figure from the British Antarctic Survey that puts these numbers in context. And so, given the short instrumental record, climate scientists have found ways to extend records using proxy measurements. So in the context of things like atmospheric CO2, we use air bubbles that are trapped in ice on the major ice sheets in Antarctica and Greenland. So this is the longest record that we currently have. This is a record from Antarctica that goes back 800,000 years. And you can see just the last couple thousand years, the last 1,000 years or so in the inset at the right. So if we look at the right side of this figure, what we see is that things were moving along pretty happily at about 285, 290 parts per million prior to the Industrial Revolution. And since then, we've had this marked increase in atmospheric CO2. The part of the figure on the left is really what provides the long-term context for this change. What we're looking at here is approximately the 100,000-year rhythm in glacial interglacial cycles. So what you can see there is about 18, 20,000 years ago or so, you start to see that line on the top really rise. That's the end of the last ice age and the addition of CO2 to the atmosphere that I alluded to before, about 90 parts per million. What you can see when you look at this figure is that by the time we got to about 1900, the year 1900, we had already hit a CO2 level that was higher than any time in the last 800,000 years. So what we're doing now is obviously far, far beyond that. That would have been the effect of early human impact on climate through agricultural land use change primarily. Okay, so let's go back to those other things. What do things look like if we look at the entire picture, right? So this figure shows the total forcing, right, which you can see is the black line, and the total anthropogenic forcing, which is the red line. And they actually follow pretty closely to one another. But I want to go through this and point out some of the other individual factors that are also relevant. So I mentioned sunspots. You see that little bump along the top there? That's the effect of sunspots, right? So when we have a sunspot maximum, we actually have a greater solar output, and we register that as a slight increase in the amount of solar radiation arriving at the top of the atmosphere. The effect of that on temperature, by the way, that cycle produces less than a 1/10 of 1 degree variation. It's usually lost in the noise of ocean atmosphere variability. Below that, you can see some other things. So for example, you can see on the top, the black snow on black carbon on snow, the contrails, the stratospheric water vapor, tropospheric ozone, the other well-mixed greenhouse gases, and then of course CO2. And then at the bottom, we see the negative forcers. Right, so what are the negative forces? Well, there are things like those aerosol radiation and aerosol cloud interactions, things like land use change, stratospheric ozone, and then the really interesting one there is the volcanic one. The volcanic one is the one that's causing these huge negative forcings that don't last very long. So for example, you can see with Mount Pinatubo in 1991, which is the last major downward excursion from volcanic eruptions. That was a very powerful eruption. It ejected a huge amount of material into the stratosphere that was able to cool the climate considerably. However, gravitational settling happens in just a couple of years, and then those effects are largely removed. So we don't have any like residual effect in the climate system now from the eruption of Pinatubo in 1991. If you go further back in time, you could see some extremely large volcanic eruptions. The one that I always like to talk to my students about is the eruption of Tambora in 1815 that led to what's referred to as the year without a summer in the Northeast US and other parts of the Northern Hemisphere. There was a 6-inch snowfall in June in New England that year, and we had frozen rivers in July in parts of New England. So it was a very, very cold winter as a result of those volcanic eruptions. So despite these large punctuations from volcanoes, you can see that in general, the total forcing in black, with the exception of those volcanic eruptions, actually matches the total anthropogenic forcing quite well. In other words, humans are currently the primary driver of changes in the Earth's energy balance. Okay, so back to the blue marble and my outline, and now we're going to shift to talking about some changes in the system. So how have these changes led to changes in observable climate? So here is our global temperature series. there are many of these to choose from because there's no easy way to take all of the point data and convert it to one number for the globe, right? This is where people that do statistics on the sphere get involved, right? Trying to think about how we might come up with one number that truly represents a bunch of point measurements. So this is what things look like. And you can see that we have the annual values in black. These are actually depicted here as departures from the 1951 to 1980 average. So those values in recent years that are about 1.0 or so, those are values that are 1 degree Celsius warmer than the 1951 to 1980 average. All right, this is at the global scale. The red line is a 5-year smoother, so it's just kind of like a moving average. And you can see that there is a kind of a gray line, a gray envelope around the series that represents the uncertainty that's a little bit larger as you go back in time, as observations are less spatially representative. So what you can see here is that, yeah, we've warmed quite a bit over this period of time. We'll talk about quantifying that here in a few minutes. And so a lot of the variability that we see in this is surprising to folks. So a good question might be, if the CO2 is increasing more or less monotonically, then why isn't the temperature also increasing monotonically? And the answer is because CO2 provides a boundary condition for the climate, but our system also has a tremendous amount of internal variability. I would venture that everyone in this room has heard of El Nino and La Nina. El Nino is a warming of the tropical Pacific. La Nina is a warming of the tropical Pacific, and La Nina is a relative cooling of the tropical Pacific. And those patterns have worldwide implications in terms of how much heat is retained in the ocean versus shared with the atmosphere and so on. So that during an El Nino, we tend to have higher atmospheric air temperatures worldwide. During a La Nina, we tend to retain more of the heat in the ocean, and the atmosphere as a result is a little bit cooler. So in general, figures that are high above that line are going to be the El Nino years, and the numbers that are below that line tend to be the La Nina years. So interestingly, it was kind of predicted, but about a year ago, we started hearing some mumblings of a pause in the climate, right? We had heard about this back in 1998 after a very large El Nino. You can see in this figure now that 1998 doesn't really even stand out. But it does if you look at 1998 versus the years that came before, right? But people said for about a decade after that that global warming stopped in 1998. And you can see now that with the benefit of hindsight, we can see exactly how nuts that statement really was. What's really important about change, though, is that it has a spatial footprint as well. So this is the anomaly just for last calendar year. And this is representative of what we see in a lot of individual years, as well as the overall pattern of warming. We have more warming in the high latitudes. That's particularly true in the Northern Hemisphere. What we can see here, actually, very interestingly, is the La Nina that we're emerging from. So notice how cold the tropical Pacific was in terms of last year relative to this longer term average. There's something very interesting going on in the global oceans today. And you might have heard about this if you pay attention to climate stories in the last week or two. Right now, global sea surface temperatures are higher for this time of year than they have ever been on record. And there's a very interesting reason for that. We've had 3 La Ninas in a row. And when you have a La Nina, you cool the tropical Pacific, but you actually warm the mid-latitude Pacific, which is a huge ocean, right? I always show my geography students, if you have a globe in your hand and you center it on the Pacific Ocean, you see the outline of land on the outside. I mean, the Pacific Ocean is almost half of our planet. So having a warmer North Pacific Ocean during La Nina, and right now we're transitioning into El Nino. So the tropics are warming really quickly. The mid-latitudes, the tropics are warming really quickly. The mid-latitudes haven't had time to cool. So as this El Nino continues, the tropics are likely to get warmer. The mid-latitudes are likely to cool off a little bit. But for the time being, we've got the mid-latitude warmth from La Nina, and we're getting the tropical warmth from El Nino. And the combination of those two things is driving the global sea surface temperature data off the charts, so to speak. Okay, so this is what precipitation change looks like. And as you might imagine, precipitation change is way more complicated than temperature change. Part of the reason for this is that you can't just assume that the world warms, you put more water vapor in the air so you get more precipitation. That's not how it works. Precipitation isn't only about presence of water vapor. It's about movement of that water vapor into regions of convergence, right? So what are the processes that are involved? How are they changing? So these are some data sets, primarily land-based, but the bottom one here actually is based on some satellite data, which is very valuable, obviously, for monitoring precipitation, fills in the gaps that we have from station-based measurements. By most estimates, we do have a positive trend in precipitation at the global scale, but it's not very strong. So you can see here, maybe in this time series, if you look at maybe 1960 to now or 1970 to now, you can see a positive trend in these data, but precipitation changes over space are quite complicated. When you look at the overall trend, what you generally see is that there are parts of the tropics that are getting wetter. That's largely because of an increase in humidity in the tropics. There are parts of the subtropics that are drying. This is because the tropics are expanding as the world warms. So when we see areas around 30 degrees north and south, right, they're going to be kind of moving more toward the poles, right, into the mid-latitudes. And the aridity that comes with that belt in our climate system will actually move north and south as that, what we call the Hadley cell, actually increases in magnitude. In the mid-latitudes, we kind of have mixed signal change. This is historical. And so in many of these cases, the signal that we expect from climate change, which is more precipitation, just hasn't emerged from the noise yet, right? And so we always say that absence of evidence isn't evidence of absence, right? So the idea being that there are many changes that we anticipate to occur in the system. Just because we haven't detected them yet doesn't mean they're not occurring. It just means that they're below the detection level. Okay, so a couple of things that I want to say about this. So Earth's average air temperature has increased substantially. So if we look at the last decade, 2011 to 2020, it was a full 1.1 degrees Celsius warmer than the 1851 to 1900 average. So that gives you a sense of how much the climate has warmed over that time. Because I know that this audience is not comprised entirely of scientists, I've taken the point of including Fahrenheit here. So this amounts to about a change of about 2 degrees Fahrenheit historically. So that's about where we are already. Most of the observed change is from human activities. And we know that with a high degree of confidence. So this is an example of what we can do thinking about some of those climate forcings and thinking about models. So we can run climate models with just the natural forcings. We can run them with just the anthropogenic forcings. We can run them with both. So that black line that you see here is the observations. If we only run our models with the natural variations, it's just flat, right? You don't actually see changes in climate that way, right? It's basically like a control case. But if you include the human and the natural causes, well, then you get an envelope that actually includes the observations. So the takeaway from that is that the only way that we can really reproduce the known climate history of our planet is by including both the natural and the anthropogenic factors. Again, you can see here that most of the observed change matches what we would expect from those anthropogenic changes. About 2/3 of the warming in this period has happened since the mid-1970s. Which I think is really remarkable. We're now warming at a rate that exceeds 0.2 of a degree Celsius per decade, right? So we're talking about a degree Celsius over 100 years, right? Now we're talking about a degree Celsius, every 40 to 50 years, right? So it is accelerating. The 10 warmest years on record. I include this in a lot of my talks, and actually I have to update it constantly because the current year is going to be in there, right? So here they are. They've all occurred since 2010. And the order of these is actually not really all that important, right? Because you're talking about at the global scale, you're talking about very small variations in heat content from year to year, right? But nevertheless, it's important that, we talked about the climate change stopping in 1998. Well, clearly not, because 1998 doesn't even make the top 10 anymore. So let's take a few minutes and think about the regional climate. How have things changed a little bit closer to home? So here's a map that shows the trend. This is very simple. This is just the trend in degrees Celsius per decade in 2-meter air temperature. And so you can see this over the Midwest. It's increased everywhere. I'm not sure how well you can see from where you are, but there are some little symbols over the points that indicate statistical significance for those that are interested in that sort of thing. The warming is significant everywhere in our region. There isn't a grid point in this data set that doesn't indicate significant warming. The warming in some parts of Illinois exceeds 3 degrees Celsius per decade, 0.3 degrees Celsius per decade, which may seem like a relatively small amount, but if you look at that over the 6 decades that are shown in this data set, you're talking about a change of 1.8 degrees C or 3.2 degrees Fahrenheit. So relative to the global average, Illinois is warming at a faster rate. Now, of course, the really interesting stuff is in the details. So one of the things that we heard about a little bit in a couple of the earlier presentations was that maximum and minimum temperatures are not increasing at the same rate. It's true in most mid-latitude locations that minimum temperatures are increasing faster than maximum temperatures, which has the effect of decreasing the daily temperature range. Okay, so one thing that's really important about this from a climate science perspective is that this really fingerprints the changes and attributes them to greenhouse-induced warming. Because greenhouse-induced warming is much more likely to affect the minimum temperatures than it is the maximums. Why? Because greenhouse gases affect the Earth's ability to lose energy. That's primarily happening at night when you don't have any input. Increasing greenhouse gases helps the planet keep more energy near the surface at night. So it results in a larger warming in minimum temperatures than maximum temperatures. In our area, one thing I'll talk about here in a minute is that we've also seen increases in humidity. And the increase in water vapor is probably the greenhouse gas that's primarily responsible for larger increases in minimum temperatures in our region than maximum temperatures. Anyway, you can see that in this map, a lot of the maximum temperatures are still statistically significant until you get up into like the northwest corner of the map that I've shown here. But for minimum temperature, they're significant everywhere, and they're quite a bit stronger in magnitude than changes in maximum temperature. A really interesting thing to folks in this room is things like changes in the growing season, right? Changes in the frost-free season. And so this is work that I've been doing with one of my students, Yao Zhue. And Yao's work is really about fruit trees, right? So she's interested in things like chilling requirements and those sorts of things. So what you can see here is on the left side, we're looking at the trend in days per decade in the last spring freeze date. In the middle, we're looking at the trend in the first fall freeze, and then the frost-free season length on the far right. And so, for example, you can see that in Southern Illinois, we've actually had a large increase in the spring, not much in the fall. So it looks like in Southern Illinois, we're getting earlier springs. By the way, I'll point out that the color bars are reversed in the first and second image. An earlier spring is from warming, and a later fall is from warming. So it makes sense to have red being both of those directions, even though they're opposite. Notice that in the northern part of Illinois, the changes tend to be smaller, but they're also more even between the spring and the fall. So that when you look at the overall change, there's not a tremendous difference between the northern part of the state and the southern part of the state. My guess, though, is that for folks that study plants, there's probably a big difference in what happens if you get the earlier warm period in the spring versus the later warm period in the fall. Nevertheless, this has implications for a lengthening of the growing season, which means a decrease in the length of the cold season, which has implications for those chilling hours that we heard people talk about presently. Some of our initial results indicate a large decrease in chilling hours throughout most of this region as we move forward in time. Another thing that I want to mention is that summertime temperatures in our region really aren't increasing very much, and that's particularly true when it comes to extremes. So this is work that I'm doing with another student of mine, Saidat Rasak Balogan, and we're looking at changes in atmospheric humidity. So what we're looking at here on the left is the change in an extreme measure of summertime temperature. This is the change in the 99th percentile summertime temperature value, T max actually. No, this is just T, sorry. Anyway, you can see that while the changes are positive over much of our area, they're not large enough to be considered statistically significant. So they don't really emerge quite from the noise yet. The one on the right shows a measure called wet bulb globe temperature, which actually is being adopted for heat stress studies. So for example, many high schools and colleges are now using wet bulb globe thermometers out on the field during sporting events to decide whether or not people should be out in gear playing football. The United States Army uses the wet bulb globe temperature to decide if conditions are okay for training exercises. Okay, so this is a measure that really reflects kind of how the human body might respond to heat stress. And so what this really represents is the fact that temperature doesn't tell the story for the Midwest in terms of changes in climate, which in our case will depend a lot on changes in near surface humidity. I think that's also very important for people that study plants because having a wetter near surface climate has important implications. These are some data that are a little bit older. So these trends end in 2017, but this is what things look like in terms of precipitation in our region annually in the top left, and then for each season along the bottom. And I'll go through this kind of quickly because I don't want to run out of time. Basically the story is that climate change in our region is leading to heavier precipitation. And most of the increase that we're seeing, about half of it has occurred during the spring in the southern part of the state. So we've got about an inch more of precipitation per decade than we did back in about 1950. And we're getting about a half an inch more per decade just in the spring alone. That has large implications if you think about things like agriculture in our region, right? A wetter spring makes it hard to get in and plant at the right time. So there are lots of implications for both plants and for commercial agriculture. Precipitation extremes are also a very ripe area of research. And this is some work that was published by another student in my group, Andrew Paxton. And the figure there on the left is showing the rainfall event that's exceeded 1 day a year. And so we kind of use that as our measure of extreme. And then we said, how often is this value being exceeded in our area? We used a very, very stringent trend estimation technique and identified the colored cells in that middle figure as being the ones that have the strongest changes in the frequency of that once a year rainfall event. Okay. And what we then did was we started tying those to changes in the frequency of atmospheric circulation patterns. So for example, you can see the circulation pattern there on the top, and you can see the actual areas within the Midwest where you get precipitation events that are larger than the 1 year event. So what we've started to do is try to actually link changes in our precipitation climate to links in the frequency of weather types that produce heavy precipitation. So this is what gets to that idea of we have a global scale change. How does that change get translated to a local impact? Well, it's through what we call the synoptic scale. It's through weather types, it's through the jet stream position, it's through all of these things that are sensitive to changes in climate at large scale. Finally, I want to show this one. I'm in the midst of a study. I'm an administrator, so I've been in the midst of this study for about 5 years. But this is a study that I'm working on that looks at watershed scale precipitation. It's very surprising to me that very few studies, if any, have considered changes in precipitation at the watershed scale, which is a very obvious scale to consider changes in precipitation. What we're looking at in this figure is the change. This is in exceedances per decade in the 10-day 1 year event. So we're talking about take the 10th consecutive wet days of the year, right? How often is that happening, right? The wettest in a given year. And it turns out that we're actually seeing significant increases, you can see through much of the Ohio Valley, including our region. We're doing this for lots of different magnitudes of event, and different recurrence intervals and so on. Okay, so we've seen in the figures that I've shown so far that both temperature and precipitation have tended toward positive values in recent times. But of course, there are a lot of nuances that I think are important to note. So first of all, statewide, Illinois temperatures have increased by about 1.5 degrees since the late 1950s. Summer temperatures have increased relatively little, especially daily maximums. As an interesting side note, humidity also limits our daily maximum temperatures in the summer. We can only get to 100 degrees Fahrenheit in Carbondale if it's dry. Now, the heat index might be 110, right? Because the temperature is sufficiently high and you have a lot of humidity, but you can't get to 100 degrees if the humidity is high, which it usually is. We have to go all the way back to 2012 to get 100-degree days in Carbondale. You remember, we were in the midst of a major drought that year that led to very dry conditions and the ability of us to get above 100 degrees Fahrenheit as a result of that. So changes in daily T-min are considerably larger than changes in daily T-max. This is something we've known for quite some time. We've experienced quite large changes in the length of the frost-free season. So we're talking about something like 3 days per decade or so, which amounts to 2 to 3 weeks of longer growing season since 1960. That's pretty substantial. For precipitation, about half of the precipitation increase so far has occurred in spring. That's been about 1/2 inch per decade. And some parts of our region have experienced increases in precipitation extremes. And we know from our own work in our group that those changes are linked at least partially to changes in atmospheric circulation patterns and their frequency. So finally, I want to finish the talk, and I've only got about 5 or 6 slides in this section, talking about future climate change and kind of what we know, what we don't know, what we can say. And most of this is going to be global scale information, but I will talk about it a little bit in the context of some of the things we've already covered. So what do we have to think about when we think about projecting climate into the future? Well, we have to think about humans, and that makes things really complicated. Demographers can't even agree on what the population trend will look like this century. And in general, more people result in higher emissions of greenhouse gases. So we have a lot of socioeconomic factors that really underpin the boundary conditions that we need to understand how the climate system will evolve. So we actually involve a lot of social scientists to help with this problem. So the idea is you have storylines or narratives, and then you come up with emissions and land use change and other climate affecting factors that are consistent with those storylines or narratives. And so here is an example from the most recent CMIP exercise. So this is from CMIP 6, which forms the basis for the latest IPCC reports. CMIP 6 adopted what are called SSPs. Those are shared socioeconomic pathways. Some of you may be familiar with the RCPs. Those are representative concentration pathways that were used in the last CMIP project and the previous IPCC reports. So what you can see here is that we have, for example, SSP 1.9 has 1.9 watts per meter squared of radiative forcing at the end of the century. Okay. As they go up from there, you can see that we have all the way up to SSP 8.5. These differ in terms of the amount of carbon that's emitted over time. So what we're actually looking at here is gigatons of carbon emitted per year. And it varies quite a lot. So these lower scenarios would be consistent with like a Paris adoption kind of approach, right? We're going to do everything we can to stay below 1.5 degrees Celsius above pre-industrial. That's going to require us to follow a path like SSP 1.9 or 2.6. On the other end of the spectrum are kind of the fossil fuel intensive scenarios, right? So those would be the ones where we're obviously emitting huge amounts of carbon dioxide, kind of continuing business as usual. And that results obviously in much, much larger atmospheric carbon burdens and a larger degree of atmospheric and climate system change. So we use these models then. We use climate models to relate those changes in boundary conditions to climate outcomes. So these changes in emissions will provide the boundary conditions for a climate model. And then the climate model will decide how much of that carbon is going to stay in the atmosphere, how much will be taken up by plants, how much will be dissolved into the surface ocean, right? All of these kinds of things are involved in our climate models now. And of course, they also represent the known range of processes that are important for understanding climate at the global scale. I mean, if you leave an important feedback or something out of these models, they're just not going to work very well. So they have to be as comprehensive as possible. And because of that, they really do push the envelope on what we're able to do. So this is what things look like with those scenarios looking forward in terms of our best estimate of change at different points throughout this century. And as you would expect, the trajectories that are associated with lower carbon emissions have much lower amounts of warming. Those that are associated with high emissions have very high amounts of warming, even approaching something like 4.4 degrees Celsius. By the way, those of you that are interested in thinking about temperatures in Fahrenheit need to multiply these numbers by 1.8 because degrees C are big degrees. And so what we're saying here is that a 4 degrees Celsius temperature change is 7.2 degrees Fahrenheit. Okay, so we're talking about very large changes at the upper end of this. Hopefully, we move away from that. So if we look at these over time, globally, this is what things look like. And you can see that each one of these trajectories has an envelope around it. And that's because when you take the same boundary conditions and run a climate model, you don't get the same output from every climate model. They all differ in the way that they handle different processes. So there's also uncertainty associated with the choice of model once you've decided which emissions trajectory you're likely to follow. Now, I think personally that this stuff is a little bit hard for the public to digest. And for that reason, I much prefer simple figure like this one. This figure shows all of those scenarios on the same plot because it turns out that the relationship between our cumulative CO2 emissions and the global average temperature is almost linear. This is really remarkable. So when we think about the difference between SSP1 and SSP5, what we're talking about is how far we move along the x-axis this century, right? So under SSP1, we're limiting our emissions to that first kind of blue-colored envelope. If we allow ourselves to go to SSP3, then we're going all the way to the end of the orange envelope, right? So we're just thinking about the temperature responding to the cumulative amount of carbon that we've emitted. This really simplifies the climate change issue tremendously, I think, right? We have a choice. If we emit a lot of carbon, we're moving all the way down to this end. If we emit little carbon, we're going to stay closer to the middle. And as a result of that, we're going to warm considerably less over time. Okay, so along those lines, we can see something important in these figures, which is what I'll refer to as pattern scaling. So what you can see here is at the top, you see the observed change per 1 degree global warming. A very important part of this is when the Earth has warmed by 1 degree Celsius, the land has warmed by more than 1 degree Celsius and the oceans have warmed by less. Okay, so that's an important characteristic. You can also see that our models do a pretty good job of simulating the warming that's associated with a 1 degree change in the climate. Now, what you'll notice is that at the bottom, we have similar maps for 1.5, 2 degrees Celsius, and 4 degrees Celsius. And what you notice when you look at these is that the pattern effectively scales. So the areas that are warmer under 1 degree of warming are also warmer under 4 degrees of warming. It's just that the whole pattern scales to a more intense level of warming. You still have the same people that warm the most and the same people that warm the least. We see a similar thing with precipitation. And so this is a clearer picture of how we think that precipitation changes. Again, changes in some parts of the tropics that are associated with convection, drying of large parts of the subtropics, and then kind of a mixed signal once you get into the mid-latitudes. You'll notice in these figures that our area is expected to get wetter. right? Not as wet as some areas, but certainly we do expect increases, and we're already experiencing increases in annual precipitation in our area as we saw previously. This figure, I think, is one that's quite sobering, because when we think about changes in temperature, and then we think about changes in precipitation, we may think, well, okay, maybe there's going to be some, it might get hotter, so plants will have more stress, but if it's wetter, then plants may also have more access to water, that sort of thing. It turns out that we expect to have problems with soil desiccation as time goes on. So in other words, what's likely to happen is that the effect of warming is that the soils themselves are likely to become drier. And that's pretty clear in this area. So some of this is going to be linked to the fact that growing season precipitation is not increasing in our area. So overall precipitation may be increasing, but it turns out that projections for the middle and end of this century actually show summers here becoming drier. So that has important implications when we think about the amount of warming that's expected and what that's likely to do to soils. So one of the previous talks referred to vapor pressure deficit, right? We're talking about the difference between, well, really you can think of this as kind of like a measure of moisture holding capacity of the atmosphere. The evaporative demand of the atmosphere is actually going to increase over time, leading to drying of soils. Okay, so the global climate and the climate of Southern Illinois alike will, with high confidence, continue to experience warming in the coming decades. There's actually little that we can do to stop warming at the global scale. There's even less that we can do to stop global sea level rise because of the long response times of some of our climate system components. So we're locked into some climate change. There's no doubt about that. But we have the ability to impact the magnitude of future climate change. But that has to happen through mitigation. It has to happen through policy. And so as a climate scientist, I give a lot of talks to a lot of different groups. And I'm almost always asked at the end, what can I do? What can I do? And so, I used to talk a lot about, individual choices and, ride a bike if you can, that sort of thing. But this problem is now a problem that's so large that we have to worry about the carbon footprints of people who frankly don't give a damn about their carbon footprint. Okay, so we're not going to solve this problem as individuals, right? We need policy. And so I always try not to be political when I give talks as well. But the reality is that if this is an important issue to you, then the way to fix it is to vote for people who also view it as an important issue that needs to be addressed. And it's as simple as that. In our region, we see pattern scaling for both temperature and precipitation, wherein those patterns are nearly identical, but more intense with additional levels of warming. I want to stop by giving a couple of key takeaways. So across climate change scenarios, so it doesn't matter if we're at that 1.9 or if we're all the way up at 8.5, we expect additional warming, and we expect that warming to result in greater extremes. It's particularly true with warm extremes. We have high confidence that warming will lead to further increases in the length of the frost-free season. Again, with high confidence. There's absolutely no reason to expect that our spring and autumn temperature trends are going to reverse suddenly based on something that we haven't accounted for. Projections also show continued increases in precipitation, although we have some evidence, as I mentioned from previous studies, that our summers may become drier overall, and certainly punctuated by larger extremes. Also, despite some increases in precipitation at the annual scale, warming is also going to increase evaporation and is likely to lead to drier soils. The second to last point I want to make is that it's very clear that we have increases in humidity in our region. And so one of the things that was mentioned in the last national climate assessment was that increases in humidity in our region in the warm season could actually lead to longer periods of dew, right? And that can lead to problems with pests and pathogens and other things like that. And finally, just kind of a closing thought based on everything that I've heard today and the reading and things that I did in preparation for this presentation is that I think we really need to think about conservation and restoration efforts in Illinois. And part of the reason for that is that we have ecosystems that are highly fragmented. And so the types of transitions that are required for plants to be able to respond are always going to work better in ecosystems that are less fragmented. And so we also can blame this fragmentation largely on land conversion, often for agriculture, but sometimes for other types of development. Okay, so perfectly timed talk. It is now 5 o'clock. So I will thank you and leave you again with the blue marble. Thanks.